Okay, we will continue with our discussion on random processes and see whether we can wind it up today, at least most of it. And let us quickly recollect what we did last time. We discussed the concepts, basic concept of a random process, and also the concepts of simplifying the characterization of a random process through assumptions of stationarity, wide sense stationarity, and ergodicity, right. So, I think that is where we were. Let us continue the discussion now. From now onwards, we will assume that we are mostly working with wide sense stationary processes, right, processes which are at least wide sense stationary, right. They may or may not be strict sense stationary, but we will assume that they are at least wide sense stationary. And please recollect that as far as wide sense stationarity is concerned, we are only required to worry about two properties, namely the mean value function and the autocorrelation function. The mean value function is going to be constant independent of time. The autocorrelation function is going to be a function only of the lag variable T1 minus T2 rather than T1 and T2. Okay. Now, therefore, these two functions more or less are a complete second order characterization of a wide sense stationary process. That they are not complete characterization, they are complete second order characterization, right. Now, let us look at the properties of the autocorrelation function in some more detail. So, from now onwards we will denote the autocorrelation function by r tau or r sub x tau or r sub y tau, etc. So, we are just looking at the properties. Some of the I am just going to mention some of these properties because they are very simple to prove. They more or less follow directly from the definition of the autocorrelation function, or at best a little bit of manipulation, and I am sure you already know this, so I will not spend too much time on it. I will just mention them. For a real process x t, x of t, right, the autocorrelation function would be real. This is also real valued, right. If it is a complex function, if your process x t is a complex valued function, then autocorrelation function could be complex valued, right. It will be an even function, it is an even function. This is already seen last time, because if I change the order of T1 and T2 in multiplying x T1 and x T2, it will not make any difference to the average value of the product, right. So, whether you write T1 minus T2 or T2 minus T1, it is the same thing, right. So, it is an even function. So, this if I replace tau with minus tau, the value will be the same. Again, for complex valued functions, the symmetry, this even symmetry will change into conjugate symmetry. So, for complex valued functions, the autocorrelation function will be conjugate symmetric. What is that? That means R x minus tau would be equal to R x conjugate tau. That is because there is a conjugation operation involved in the multiplication when you take the autocorrelation function of a complex valued random process. Okay. Conjugate symmetry is also sometimes called Hermitian symmetry. And the third property, so this is property number 1, this is property number 2, and property number 3 is that it is maximum, autocorrelation function is maximum at tau equal to 0, right. Property number 4, if the random process x t happens to be periodic, so for periodic random processes, the corresponding autocorrelation function also will be periodic. Okay. These are fairly straightforward properties to prove, just enumerating them for the sake of completeness, so that you are familiar with these things. 5, this is important, very important, the Fourier transform of the autocorrelation function. So, the Fourier transform of the autocorrelation function which we have seen is nothing but the so called power spectral density function, right. And remember how we define the power spectral density function? It was expected value of Fourier transform of x t magnitude square, right. So, we are taking the expected value of some squared quantity, right. So, what can you say about such an expected value? It will always be positive, right, and therefore, the Fourier transform of the autocorrelation function of any random process will always be positive, right. It will be real valued positive quantity. Unlike the Fourier transform of an arbitrary function which can even be a complex valued function, the Fourier transform of an autocorrelation function would always be real valued and positive, right. So, is non-negative, actually more generally we should say it is non-negative for all frequencies, right, and that is one of the important tests for, let us say, checking whether or not a given function would be an autocorrelation function of some process or not, right. We take its Fourier transform, if it is a positive function for all frequencies, then it is likely to be an autocorrelation function of some process or the other. Then we already know, is this okay? This is understood by everyone. The motivation why this property comes. This comes from the definition of the power spectral density function, which we define to be the expected value of some square quantity, right, and therefore must be positive. And we already seen that the power spectral density function and the autocorrelation function are Fourier transform pairs, that is by Wiener-Khinchin theorem, right. So, also the value of R0, which we also said is maximum, incidentally for a periodic autocorrelation function the peak will repeat itself at periodic intervals with the period t, whatever is the period, but in general R0 is maximum and its value is equal to, it has a physical significance, it is equal to sigma square, the variance of the process at time t or for all time. We are, since we are considering white sense stationary processes, the variance will be the same for all time instants. So, it is a total, which we sometimes also call the total average power. Right. Why? Because as you can see, if you remember, R tau would be the inverse Fourier transform of the power spectral density function, right. Right. So, if I put tau equal to 0, what do you get? R0 equal to integral of Sxf, that is the area under the density function, right, and therefore, it is the total average power. And the last property that I like to mention here is that in general for random processes, if you consider the limiting value of R tau as tau tends to either plus or minus infinity, right, that is we are giving, here is the general nature of the autocorrelation function. What kind of function would be the autocorrelation function? In general, as we approach infinity on either side, plus positive side or negative side, the value of the autocorrelation function would tend to, this limit will be equal to mu x square. So, R x tau, if I put mu x square, where mu x is the mean value. Okay. And if the process happens to be 0 mean, then what will happen to this limiting value on either side? It will tend to 0. Now, this I am not proving, but it is very simple to prove, but intuitively it is even more simpler to appreciate. What we are saying, suppose it is a 0 mean process, just for the sake of argument, what we are saying is every autocorrelation function for a 0 mean process would tend to 0 as tau tends to infinity. Does it make intuitive sense? What does Rx, just remember, try to ask yourself, what does the value of R tau represent for a given value of tau? It represents the cross correlation between two random variables which are sampled, which are obtained by sampling the random process at 2 time instants which are separated by tau seconds, isn't it? This is a correlation between 2 random variables which are separated by tau seconds, and what this says is the larger you make this separation, the smaller the correlation between them, and it will become 0 as tau tends to infinity, right. That is, if the separation between them becomes very large, there is every reason to expect that their relative values will have absolutely no correlation with respect to each other, right. So that's basically, that makes a lot of sense. If it's a truly random process, it should happen that way, right. Close by points would have a larger correlation. That is why R0 is a maximum, right, and then it starts to decay and it decays to 0 on either side. Okay. So typical form, yes please.
So what if this represents a periodic function?
If it is a periodic function, then this will not be true, right. This property is not valid for periodic autocorrelation functions. This is only meant for a periodic autocorrelation functions. So basically what we are saying is, you are right, the autocorrelation function typically will have natures like that, decays to 0 as tau tends to. This is a plot of a typical autocorrelation function as tau tends to infinity or minus infinity. It has to be even symmetric, for if it is, and its real value for a real valued process, and so on and so forth. Okay. At this point, having defined the basic concepts which characterize a random process, it is now possible for us to look at a very important special process which we shall be using in modeling noise in communication systems, right. And in fact, the process, this particular random process is known by the name of a white noise process, right. So let me define a process, a particular kind of process which is called a white noise process. Before I take it up, I just like to re-emphasize the fact that the autocorrelation function and the power spectral density function, they are equivalent second order descriptions of the random process, isn't it? Because they are Fourier transform pairs. If you give one, you know the other, right. So they are both second order descriptions, and secondly, these descriptions are that we discuss are independent of what kind of density function the process has, right, because we are only looking at the first two moments of the density function, the first order movement which is the mean function, and the second order movement which is the autocorrelation function. You could have any density function, right, and you could have random processes with different density functions, different joint density functions having the same second order properties, right. So that is something that you have to keep at the back of your mind, that when I am discussing only second order properties, we are ignoring the density function properties, because we are ignoring the detail. We are only looking at these two gross properties. The detailed properties are not known to us, or we are not talking about them at least. Okay. Let me come back to the white noise process. A white noise process is one, it's really, the definition is very simple, for which the power spectral density function has this form. It is constant, and this is just a value, arbitrary value or arbitrary notation for the constant, is usually denoted by n sub 0 by 2 for all frequencies. Okay. For all values of the frequency f, the autocorrelation, the power spectral density function is a constant. So the power density function plot as a function of f looks like this. Okay. And now you can see where the name comes from. The name comes from the fact that all frequency components are present in equal measure. So the analogy comes from white light, right, where a large number of frequency components constitute the white light. Okay. So that is where the name comes from. If the process is, if the power spectral density function is not flat, then if you want to call it, you can call it a colored random process, a colored noise process, because it is not So, it is just as against white, right. So, if it is not flat, we call it, sometimes we just loosely call it a colored noise process, right, and there are various kinds of colors that one can have, but usually we simply call it a colored noise process. Now, what will be the autocorrelation function of this process? What is Rx tau? Of a white noise process, what is Rx tau? It will be delta function. It will be N0 by 2 delta tau, right, because this is the Fourier transform pairs. The Fourier transform of this is equal to this, the inverse Fourier transform of this is this, right. So, the autocorrelation function therefore plot looks like this. This is delta tau, sorry, this is tau, and this is N0 by 2 delta tau, tau equal to 0. The delta function occurs at tau equal to 0. This N0 by 2 is more or less a standard notation used in communication theory. It essentially says this is called two-sided power spectral density value. The value of N0 by 2 is called two-sided power spectral density. In as much as these negative frequencies are only abstract entities, the corresponding one-sided spectral density is sometimes called N0, is denoted by N0, the twice of this, right. That is, if you reflect the negative excess also on the, or if you only talk in terms of positive frequencies, right. The total power at frequency in a neighborhood of frequency f, right, will be actually the sum of these two areas, right. Remember that, because every real signal with frequency f will also have a component as minus f. So, really speaking, if you want to compute the power contained in a region between f to f plus delta f, you have to add up this area with this area, right. So, N0 by 2 delta f plus N0 by 2 delta f, which will become N0 delta f, right. So, N0 is sometimes called single sided power spectral density for the white noise process, and N0 by 2 would become the double sided power spectral density. These are just some general terms which are used, and therefore you should know. Now, this is a very convenient model for many physical random processes that we come across in communication theory, but remember, it is only a model. Why? Because such a process cannot physically exist. Can you see that? Why can it give one reason why it cannot physically exist? That is one way of looking at it, but let us look at it in a slightly different way. What is the total power under this process? Infinity, right. No physical process can have infinite power, right, because it is the area under it is infinity, right. Alternatively, if you look at the autocorrelation domain, what does it say? That other than the fact that xt would be related, xt will be correlated with xt, if you move even a slight in the time domain or along the time axis, if you move even slightly, and if you look at two samples which are very, very close together, but not the closeness is not equal to 0, right, they will be uncorrelated, right. So, for such thing to happen, for such wide jumps to occur, the process must have infinite power, otherwise it will be correlated, right. Otherwise the process will have some degree of smoothness, and if there is even a minute degree of smoothness, this can never happen, right, in any time function that you may deal with, right. So, basically infinite power or such an autocorrelation function are idealizations which will never occur in practice. However, in spite of the fact that this is so, it is convenient to model many physical processes in communication theory with this model, because they more or less satisfy the broad characteristics that this model assumes. For example, the kind of noise that we deal with in communications, the thermal noise, has a very large spectrum, very wide spectrum, and more or less it is flat over that spectrum. So, it does not really go up to infinity. Infinity is anyway an abstract term. It goes very wide, much larger than the bandwidth of the signals that you are working with. So, for all practical purposes, you can model that as white noise. Okay. So, even though in practice it is not truly white in the true sense of the word.
So, when we say white noise, we consider all the noises actually better. Like short, we have thermal noise, short noise.
Most thermal noise, short noise, and various other kinds of noise many of them can be modeled as white. But there are situations where we have to deal with a non-white model. Okay, there are situations. So it doesn't mean that we will always have in real problems we always need to work with only white noise. Right? There are situations when we have to look at the actual spectrum of the noise, which is typically not white in some situations. Right? Okay. At this point, I think it is important for us to understand one additional set of relations which we typically need to work with. Many times you will be faced with, when you are analyzing systems with random inputs. You know, after all, our purpose of doing this review right now is to have the necessary tools to analyze the performance of communication systems in the presence of noise. And if you remember whatever we have discussed so far, most communication systems will involve, one of the major components of any communication system would be filters of various kinds. Right? You are doing a lot of filtering here and there. Right? So, you like to know if there is a certain kind of process, that is random process, which is input to a filter, what kind of random process will be the output of this filter. Right? So, you like to know these relationships. So, let us look at these relationships, that is what happens when you transmit a random process through a linear system. Right? Through a linear system or through a linear filter. So, we have if linear systems with impulse response h of t, input is a random process x of t, output is some random process y of t. Okay. So, in as much as we are concentrating only on the white sense stationary processes, that is, we are going to assume that x t is a white sense stationary process. We will also try to characterize y t in terms of first two movements. Of course, we will it can be shown that y t also would be white sense stationary. Maybe it will be obvious, but even if it is not, it can be shown. Right. So, that means given the mean value function and the autocorrelation function of the input process, you would like to find out what is the mean value function and the autocorrelation function of the output random process. That is the concern. Okay. So, let us look at the mean value function. How is y t related to x t? Through the convolution relation. So, basically that is our starting point. So, if I look at expected value of y t, that is the mean value of function of y t. So, first let me express y t in terms of x t is h tau x t minus tau d tau, right. So, if I take the expected value of this, basically what are we saying? Take the expected value of this integral or this convolution relation, right. H t is a deterministic filter, H t is a deterministic function, and expectation is also a linear operator. It is a linear operator with respect to the density function of the process, right. And because it is a linear operator, under certain conditions you can carry the interchange these two integral operators, the integral operator corresponding to the expectation operation and this integration, right. So, I can carry the expectation operator inside the integral, write the expected value of the product of these two, but h t is not random. So, we can keep it like that, h tau, and really speaking the averaging will operate on the process x t, right. We are using the linearity property of the expectation operator. So, but what is this? This is by definition the mean value function of the, this is mu x t minus tau, and since we are assuming white sense stationarity, right, what will be the value of mu x t minus tau? It will be a constant, right. So, it will be minus tau to tau, minus infinity to infinity h tau into mu x tau. mu x is a constant, it comes out of the integral, so that's what you have, right. So the mean value at the output is the mean value of the input. So that shows that if the input process is stationary up to first order, the output process also will be stationary up to first order, because this is not a function of time, right. Mu xt was not a function of time, you find that mu yt is also not a function of time, right, because this is going to be a fixed value, some number, and what is that number? You are multiplying mu x with the area under the impulse response. Can you express it in terms of frequency domain relation? This is equal to, so mu y is equal to mu x into x0, right, isn't it? Because this is nothing but capital H of 0. H of f is h tau e to the power j 2 pi f tau. You put f equal to 0, you get this, right, and that is intuitively very appealing, because what is it? You can think of the mean value of the input as a DC component of the input process, right. It is a zero frequency component. Mean value is intuitively you can consider it to be the zero frequency component, right. And so what does it say? That the mean value of the output is the mean value of the input multiplied by the response of the system at DC response of the system, right. So that is the first relation, very simple basic relation. So if you know the frequency response, in particular if you know the frequency response at f equal to 0, that is how the mean values will be related. So this relationship is very simple. However, the next one is not that simple, but does not matter, it is still not very complicated. So let us look at the autocorrelation function now. So we want to find out Ry du, which by definition is expected value of yt into yu. Now you might have noticed that I have not deliberately written t minus u, because I have not proved yet that the output process will be stationary, right. I know that the input process is stationary, but we have to also see whether the output process turns out to be stationary or not, right. So we will start with writing like this, and if it turns out to be a function of only t minus u, then it becomes a stationary process, right. So let us look at this. This by definition is, now just we will just substitute the values of yt and yu. This is a fairly mechanical process. Use a dummy variable tau 1, x t minus tau 1 d tau 1. Use a dummy variable tau 2, x u minus tau 2 d tau 2. Expected value of this, right, straightforward. Just substituting for yt, substituting for yu. Use different dummy variables to differentiate the two integrals. Can write this like this. I am taking the linear operator expectation operator once again inside, combining it with these two random entities. These are the two random entities. So the expectation will now work on the product of this and this. So x t minus tau 1, x of u minus tau 2, that is it. Okay. Of course, certain conditions are required to be satisfied for this to happen to be valid, but we will assume those conditions are valid. The basic conditions are that h of tau should correspond to a stable system and x of t should be a finite energy process or a finite power process, right. These are the conditions which are generally required. We will not go into details. Okay. So this is t tau 1. Is that okay? I think these are, it's fairly mechanical manipulation. You should not have any difficulty. And what is this quantity? This expectation, this is Rx t minus tau 1. Okay, at the moment let me write the general expression u minus tau 2. If we assume it is a stationary process, right, then it will be a function only of this minus this, right. So, if for WSS or for white cell stationary xt, let's define tau equal to t minus u, right. So, this becomes, can you see that it is a function of t minus u, right, because it will be a function of this minus this or this minus this, right. So, this becomes, I can write r y tau instead of writing r y t u, I can now write r y tau because it is a function only of t minus u, would be equal to, just rewriting this, right, rewriting this relation. You have h tau 1, I think you can look at your notes and check. You have h tau 2, and what will you write here? R x, take the difference, it will become tau minus tau 1 plus tau 2, right, d tau 1 d tau 2. Okay. So, as you can see, it is a function, this tau 1 and tau 2 will disappear after these two integrations have been done. So, you will be left only with the function of tau, so r y is a function of tau, right. So, which implies that y t is also WSS. So, if you pass a white cell stationary random process through a linear time invariant filter, right, because h t was a linear time invariant filter. In fact, that is the reason the output process is white cell stationary. If, for example, if the filter was a time varying filter, even though the input process was white cell stationary, the output process then may not be white cell stationary, because of the fact your filter impulse response keeps varying with time, right. So, for the output process to be white cell stationary, the input not only the input process should be white cell stationary, the filter to which you are passing it should be time invariant. So, time invariance is the clue which we have used here. Okay. So, what do you find? You find there is some kind of it seems like this relationship that you have looks complicated, but actually it is a very simple relationship, right. I will not go through the details, I will give this as an exercise. It will be good exercise for you to complete, because these are, it's a repetition of the same steps that I have done so far, right, and that will help you to see the relationship in a slightly better light. Instead of directly looking at the autocorrelation function of the output, right, here is your system that you are working with. What we have done so far is we have related the output autocorrelation function with the input autocorrelation function. Go through a two-step process. First, try to relate the cross correlation between the input and the output to the autocorrelation function of the input. That is, consider expected value of xt into yu rather than yt into yu, right. Then you have to only deal with one integral rather than two integrals, isn't it? I should have defined the concept of cross correlation function, which I have not done, but let me complete that. So, just like you have the autocorrelation function of a process, which is Rx tau equal to Rx t1 t2 equal to expected value of xt1 into xt2, I can define a cross correlation function between two processes x and y, any two processes x and y, in the same manner. What do? I sample the random process xt at the time instant t1, sample the random process yt at the time instant t2. I have two random variables now, xt1 and yt2, take their cross correlation. So, that is the definition of cross correlation function of two random processes. So, it will be xt1 into yt2. Okay. So, basically what I am suggesting is first find out for this picture the cross correlation between these two processes, the input process and the output process, right, and then find the output autocorrelation function in terms of this cross correlation, right. If you go through this two-step process, let me just give you the result, please verify them, then this whole relationship becomes much more meaningful. So, what you have to verify is the following: show that R y x tau is equal to R x tau convolved with h of minus tau. Okay, very simple relation. And of course, unlike the autocorrelation function, the cross correlation function does not have that even symmetry property, right, because we have different processes. Now, if you change the order of xt and yt, it will make a change, it will be a different function, right. So, I mean there will be some relationship, but it will not be a symmetric relationship. For example, if I change the order, I first take x and then take y, right, then you will find that the relationship is like this: R x tau convolved with h tau. So, they are equivalent. Okay. The general relationship between R y x tau and R x x tau, R x y tau would be this. You see the difference? We are not saying R y x tau is equal to R y x minus tau, right? It is R x y minus tau, right? Which is obvious. Again, just look at the definition; these things will more or less follow from there. Okay, so this is one relationship. You are able to express, what does it say? The cross correlation between the input and the output is the autocorrelation function of the input convolved with the impulse response, either directly, depending on whether you are having this kind of cross correlation, or with a mirror image of the impulse response, right, around the origin, right. In the second step, please show that you can express excuse me, R y tau or R y tau, that we usually write simply R y tau to simplify, can be written as R y x tau convolved with h tau, right. How will you do this to show this? You start with expected value of y t into y t plus tau. That is the definition of R y tau, right. Then substitute only for y t plus tau, keep this there in terms of x t, right, and go through the process. So, you will ultimately end up here. So, if I combine this relation with the previous relation, which was this, what do you get? If I combine these two relations, what will you get? R y tau is equal to, I am substituting for R y x tau as R x tau convolved with h minus tau, and this convolved with h tau, and that is precisely what this relationship is that we defined. Okay. So, now you can look at this relationship in a much simpler manner. It is really a double convolution of the autocorrelation function of the input with h minus tau first and h tau later, or the other way around, okay, because convolution is a commutative operation. So, this relationship, which looks rather complicated, is actually this, which is much more appealing.
So, if we substitute for y of t plus tau, then what about y of t? Even we will get in terms of y of t, we have to substitute even for y of t, so otherwise we will have an x of t term and
No, what I am saying is that is right. when you substitute for x of y of t plus tau, there will be one y term and one x term. That is what will lead to r y x term. Right? Is it okay? Okay. Now this is therefore the relationship between the input autocorrelation function and the output autocorrelation function. Incidentally, these relationships are very useful. Let us look at this relationship for example, right, which you can prove very easily, which I am sure you will be able to prove in exactly one step. Or let us say look at this relationship. This is extremely useful, and this we will discuss the application of this very briefly. This tells me that if I cross correlate the input and the output random processes, what I will see is this convolution. Suppose I choose my input autocorrelation function to be a white noise process, input process to be a white noise process. What will be the corresponding autocorrelation function? Autocorrelation function delta tau, some constant delta tau. What will be the cross correlation of input and output now? It will be simply h tau, right? So what is the result? If I feed a white noise process at the input to a linear time invariant filter, the cross correlation between the input white noise and the output noise, which may not be white, which will not be white actually, right, would the cross correlation function would be proportional to the impulse response of the system. So this gives me a method of finding the impulse response of the unknown system experimentally, right. I feed white noise at the input to this system, look at the output random process, cross correlate these two processes, right, and the result of cross correlation will identify the impulse response for me, which was otherwise not known to me. Let us say it is not known to you, right. So this is a very useful relationship. Where can I use it in communication systems? Channel, right. The typical unknown thing in a communication system is the channel system through which the signal is being passed, right. So many physical communication systems actually use this method to identify the channel impulse response. For example, your GSM standard, which you are using in the mobile telephony, transmits wires in the form of packets, information in the form of packets. Every packet has in the middle of it a training sequence, right, which is essentially some kind of a pseudo noise sequence, pseudo noise white sequence, right, which is passed and therefore when you look at the output of the corresponding to this training sequence of the receiver knows or can find out through cross correlation between what was transmitted and what is received, right, the estimate of the channel impulse response, and that is then used to further process the signal to get your signal nicely. Okay. So this relationship is extremely useful. You appreciate what I am saying? We will discuss it further if necessary. Now finally, this relationship implies a corresponding relationship in the frequency domain, right. Let us look at that relationship. Let us take the Fourier transform of both the sides. So what will be the Fourier transform of this? The power spectral density function of yt, right. Fourier transform of r y tau will be syf. This will be sxf. Convolution in time domain will reduce to multiplication in the frequency domain, right. So what will be the product here? Sxf into h of f, and what will be the Fourier transform of this? H conjugate of f, right. So what do you get? Hf into h conjugate f, which is hf mod square. This is the corresponding very simple, intuitively appealing frequency domain relationship. Okay, that is the output power spectral density function is obtained by multiplying the input power spectral density function by magnitude square of the transfer function, right. Makes sense, because power spectral density function is a positive function. You must multiply it by a positive number to make sure that it is always a positive number. So it makes a lot of sense. Any questions? Any questions so far? No. Okay. Finally, let me spend some time on, if I am returning to density functions. So far, when I was discussing purely in terms of white cell stationarity, I had ignored the concept of density function, because I was looking at a second order characterization of the process, right. But it is useful to know, which I mentioned before to you, that many physical processes the density function happens to be Gaussian, right. So, we need to also look at these functions or these processes in some more detail. So, in fact, most of the time the kind of noise process we will deal with will model the second order properties by saying that it is a white process. That means the power spectral density function is flat, but we will not leave it at that. We will also say, we will say something about the density function. We will say it is a white noise, it is a white Gaussian noise. So, now we are not only talking about the second order property, but we are giving some more detailed information, that is, it is the density function associated with that is somehow Gaussian. We understand the notion of a Gaussian random variable. The notion we like to understand is that of a Gaussian process. When we say a process is Gaussian, what does it mean? We know that when a random variable x is Gaussian, what it really means is that the density function is this. Right. So, the question is, what do we mean by saying that xt is a Gaussian process? What does this mean? That is what we like to understand a little bit. Okay. Okay. To start with, let me recap one very important property of a Gaussian random variables. Suppose x1, x2, xn are all Gaussian random variables. You have a class? Okay, we will just take care of that. Suppose these are Gaussian random variables, then if I construct a linear combination of these Gaussian random variables by saying that by constructing y in terms of xi's and gi's are some arbitrary coefficients of linear combination I going from 1 to n, right, then y will be Gaussian, right, we know this. Now, I will say this in a slightly different way. We will define a set of random variables x1, x2, xn to be jointly Gaussian. This is the definition now. We will say that x1, x2 to xn are jointly Gaussian, such that if I take any linear combination of these, the output random variable, the resulting random variable is Gaussian. So, if this is Gaussian for an arbitrary set of coefficients gi, for arbitrary choice of gi's, right. This will form the basis for our definition of a Gaussian random process, which I will take up next time. Thank you very much.